What are the trends in physical properties? One is atomic and ionic radii, the other one is ionization enthalpy, the third one is electron gain enthalpy, and the fourth one is electronegativity. So the electrons are added to the same shell, so that would be K shell or L shell or M shell. So when you go across a period, the shell will be the same. Which of the following has the most negative and least negative electron gain enthalpy among the elements that is mentioned? Phosphorus, sulfur, chlorine and fluorine. Hello dear students, I am Roja, your chemistry lecturer from Vidhyaashram PU College, the Temple of Excellence, Mysuru. So we shall continue the chapter Classification of Elements and Periodicity in Properties. So in the last class we have studied about why do we need to classify elements, then genesis of periodic classification, then modern periodic law and the present form of periodic table, and also about nomenclature of the elements with atomic number greater than 100. In this session we shall study about periodic trends and properties of elements, both physical and chemical properties. So let us study one by one, that is periodic trends and properties of elements. So the periodic table shows many observable patterns in both physical and chemical properties of elements. So now we shall study what are the trends in physical properties. One is atomic and ionic radii, the other one is ionization enthalpy, the third one is electron gain enthalpy, and the fourth one is electronegativity. So now we shall study what is atomic radius. Measuring the exact size of an atom is difficult because electron cloud has no sharp boundary. So instead we estimate atomic size by measuring distance between the atoms. So therefore there are ways to define atomic radius. One thing is covalent radius and the other one is metallic radius. So covalent radius is the half of the distance between the two atoms that is joined by a single covalent bond. So this, if two atoms are joined together or combined together, so that half of the distance between these two atoms are taken as covalent radius. For example, in chlorine atom the bond length is 198 pm, that is picometer. So the covalent radius of this single chlorine atom is 99 picometer. So half of this length. Then metallic radius is half the distance between two adjacent atoms in a metallic crystals. So it is only for the metallic crystals. Say for example, when atoms are joined together, when they are placed adjacent to each other, so the half of the distance between two adjacent atoms are taken as metallic radius. For example, in solid copper, that is, so when copper and copper are placed adjacent to each other, the distance would be 256 picometer, but the metallic radius would be half of it, so it is 128 picometer. Then what would be the atomic radius across a period is, across a period atomic radius decreases. What is the reason for decreasing of atomic radius are? So the electrons are added to the same shell, so that would be K shell or L shell or M shell. So when you go across a period, the shell will be the same. So that means if nuclear charge increases, it pulls the electrons towards itself. So nucleus consists of positively charged particles, so that is the reason electrons will be attracted towards itself. For example, in period 2, that is one which has lithium on the top, will have the atomic radius 152 picometer. So when it moves towards right side, that is towards fluorine atom, the atomic radius decreases. So what happens to the atomic radius when you go down the group? So atomic radius will increases. What are the reasons are? New electron shells are added, so that will increase in the principal quantum number, that is represented by N. Shielding effect reduces the pull of nucleus on outer electrons. So the shielding effect between the nucleus and the outer electrons will be reduced. So group 1 elements from top to bottom, that is when it starts from lithium, that group ends with a cesium. So lithium has 152 picometer. When you go down the group, it increases to cesium 262 picometer. And how about noble gases? Their atomic radii are unusually large if measured by van der Waals forces, not covalent. Hence noble gas radii are not compared with the covalent radius of other elements. So now we shall see what about the ionic radius. When an atom loses electrons, it forms cation, that is positively charged ions. When an atom gains electron, it possesses negative charge, that means it is called as anion. The size of these ions, called ionic radius, can be estimated by measuring the distance between cations and anions in ionic crystals. So, the general trends that goes with the ionic radii across a period and down a group is, ionic radii follow the same general trend as atomic radii, that is, across a period it decreases and down the group it increases, and reasons would be the same as atomic radii. So, when you consider ions separately, cations will be smaller than the atoms because fewer electrons would be present and therefore there will be a small nuclear charge. Electrons are pulled in more tightly because most of the electrons are already lost and the fewer electrons will be pulled towards the nucleus. So, sodium atom has 186 picometer, and sodium ion, when it loses electron, the ionic radii would decrease to 95 picometer. So, when it comes to anions, they will be larger than the actual atoms because anions are formed when electrons are added to the outermost shell. So, extra electrons will be responsible for the greater electron-electron repulsion. Effective nuclear charge per electron will decrease, and therefore, fluorine atom, if the length is 64 picometer, the ionic form of fluoride ion will have 136 picometer. So, next is isoelectronic species that comes under ions, that is, those species are the ones which consist of atoms or ions with same number of electrons. So, such type of species are called as isoelectronic species. For example, oxygen with 2 minus ion, fluoride ion, sodium ion and magnesium ion will all have 10 electron in its outermost shell, and therefore, these species will be called as isoelectronic species. Now, what are the features of these isoelectronic species are? Their sizes depend on nuclear charge, that is the atomic number. Higher positive charge, smaller will be the ion. Higher the negative charge, larger will be the size of the ion. Order of size will be from largest to smallest, that is, it starts from oxide ion, which is greater than fluoride, which is greater than sodium ion, and which is greater than magnesium ion. So, the third criteria is ionization enthalpy. So, we shall know what is ionization enthalpy. It is the minimum energy required to remove one electron from an isolated neutral gaseous atom in its ground state. So, first ionization enthalpy is known as by this reaction. So, it says the minimum energy required to remove the electron. So, if this is a neutral gaseous atom, when electrons are removed, it gives positive charge for the element, then the electron will be removed. And the second ionization enthalpy takes place in such a way, the atom having a positive charge, from there if one more electron is removed, then it possesses +2 charge, then one electron will be removed. So, that will be the second ionization enthalpy. Ionization enthalpy will always be positive since energy is needed to overcome the attraction, and it increases with successive removal of electrons from first stage, second stage and the third stage it goes on, because it gets harder to remove electrons from positively charged ions. So, what will be the trends in a periodic table in terms of ionization enthalpy is, across a period ionization enthalpy increases because there will be more of a nuclear charge and shielding effect does not increase much when you go across a period. Electrons will be held more tightly. So, that is why the ionization enthalpy will increase. When you go down a group, it is the ionization enthalpy will decrease. That is because outer electrons will be farther from the nucleus. So, what happens, more shielding will be by the inner electrons, and therefore, it becomes easier to remove the electrons. So, therefore, ionization enthalpy will decrease. So, there are few exceptions like anomalies between boron and beryllium and oxygen and nitrogen. So, what is that exception is, boron has an atomic number 5, beryllium has atomic number 4. So, from beryllium the electrons to be removed is from 2s. So, but then that will be closer to the nucleus, so it gives a lesser shielding effect. When it comes to boron, electrons removed will be from 2p orbital. So, that will be more shielded by the inner electrons, so it is less tightly held by the nucleus. So, therefore, ionization enthalpy for boron will be lesser than compared to ionization enthalpy for boron will be less compared to the ionization enthalpy for beryllium. So when it comes to oxygen versus nitrogen, oxygen has got atomic number 8 and nitrogen has got atomic number 7. So the electrons will be removed from 2p3. 2p3 in the sense maximum of electrons to be filled in p orbital is 6, but there are 3. So that means 3 orbitals are half filled with single electrons. So electrons are evenly distributed in separate orbitals, so that gives stability to nitrogen element. But when it comes to oxygen, it consists of 4 electrons in 2p orbitals. So one orbital will have electron pairing and the other 2 will be single. So there causes repulsion. So this becomes easier to remove one electron from the oxygen. So therefore ionization enthalpy for oxygen is less compared to that of ionization enthalpy of nitrogen. So now we shall know what are the factors that is affecting the ionization enthalpy. First thing is nuclear charge. So higher the nuclear charge, higher will be the ionization enthalpy. Distance of valence electron from the nucleus. So larger the distance from the nucleus, lower the ionization enthalpy. So shielding effect, more the number of inner electrons, lower will be the ionization enthalpy. So fourth factor is electronic configuration stability. That means half filled and fully filled orbitals are known to be given extra stability to the elements, and therefore it will be higher the ionization enthalpy. Okay, the next criteria is electron gain enthalpy. So the enthalpy change, enthalpy is nothing but heat energy. That heat energy change when one electron is added to an isolated gaseous atom to form a negative ion, it's called as electron gain enthalpy, and units used to represent is kilojoule per mole. So that is what is shown in the reaction. So when one electron is added to the element neutral gaseous atom, so it possesses negative charge. This can be either of exothermic or endothermic reaction. What happens to the electron gain enthalpy when you go across a period and down the group R? Across a period it becomes more negative, that is because increasing effective nuclear charge, again nuclear charge will play a major role, and decreasing the atomic size will give stronger force of attraction for the added electron. Down the group when you go, it becomes less negative, that is because increasing atomic size and shielding, that is because of added electron that will stay farther from the nucleus will be the reason. And in special cases, that is like in anomalies, and in special cases anomalies like oxygen and fluorine have less negative electron gain enthalpy compared to that of sulfur and the chlorine respectively. So what are the extremes in the periodic table is, so most negative electron gain enthalpy would be possessed by halogens of group 17, especially chlorine element. Least negative electron gain enthalpy would be possessed by noble gas of group 18 element, and some alkaline earth metals are also included. So now we shall understand which of the following has the most negative and least negative electron gain enthalpy among the elements that is mentioned: phosphorus, sulfur, chlorine and fluorine. The answer would be most negative will be chlorine and least negative will be phosphorus. The phosphorus will be a larger atom, but then it would possess lower net nuclear charge. So that is why it possesses less negative. Sulfur will be more negative compared to phosphorus, but then fluorine, when it comes to fluorine, the atomic size of the fluorine will be very small. So therefore it leads to stronger repulsion in 2p orbital. So it is again less negative compared to chlorine. But when it comes to chlorine having a shell number 3, larger will be the space and stronger will be the attraction and less repulsive forces between the electrons. So therefore it leads to most negative electron gain enthalpy. So the order goes like this: sulfur is less negative compared to fluorine and fluorine is less negative compared to chlorine. So the most negative is chlorine. So the other trend is electronegativity. So electronegativity is a qualitative measure of the ability of an atom in a chemical compound to attract shared pair of electrons towards itself. So it gives, it defines the ability to pull the electrons towards itself. Unlike ionization enthalpy or electron gain enthalpy, electronegativity is not measurable directly, so it requires different measuring scales. What are the other features are? Electronegativity is not an energy term but a relative property, closely related to non-metallic character because it pulls the electrons towards itself. Higher the electronegativity, stronger tendency to attract electrons. Lower the electronegativity, metallic behavior would be exhibited by the elements. So, what happens across a period and down the group are, across a period electronegativity increases because when you go from left to right, the non-metallic character is going to increase. Reason for that is effective nuclear charge increases and therefore atomic size will decrease. So, since atomic size will be decreased, stronger will be the pull on the shared electrons towards the nucleus. Then metallic character decreases, so non-metallic character is going to be exhibited by the elements. And when you go down the group, electronegativity decreases. That is the reason because atomic size will increase and therefore more of the electrons will be added to the outermost shell, which leads to the larger atomic size. And because of this reason, there will be weaker force of attraction between the nucleus and the outermost electron. So, the metallic character increases and non-metallic characters are going to decrease down the group. So, let us see what will be the relationship between. So, now let us see how electronegativity is going to be related with metallic and the non-metallic character. So, higher the electronegativity, stronger will be the non-metallic character. Lower the electronegativity, stronger will be the metallic character of the elements. Example, from left of the table if you see, it is sodium, potassium and calcium, it will have lower electronegativity property. From right of the table, from chlorine, oxygen, fluorine will have higher electronegativity and that leads to metallic and non-metallic behavior of the elements. So, when they have low electronegative energy, therefore, it possesses metallic property again. If they are high, then it possesses non-metallic properties. So, that was about periodic trends in physical properties. Now, we shall study periodic trends in chemical properties. So, first thing is periodicity of valence. Valence in the sense the number of electrons that is present in the outermost shell which is able to gain. What do you mean by valence is, it is the number of electrons that is present in the outermost shell which has the property of gaining of electrons or donating of electrons, that depends on the elements. So, the valency of electrons are explained by electronic configuration. So, the general rule for representative elements, that is S and P block, are together called representative elements or main group elements. So, the rule is valence is equal to number of outermost electrons. So, if the number of outermost electron would be less than 4, then that will be the number of valence for that particular element. If the valence electrons are more than 4, then the valence is calculated by 8 minus number of outermost electrons. So, if outermost electrons, if it is more than 4, then it has to be subtracted from 8. Let us see with the examples, that is carbon having the electronic configuration, that is outermost electronic configuration is 2s2 and 2p2. So, the valence of these electrons will be 4 and that will be the valence. It can either lose 4 electron or gain 4 electron. Oxygen has outermost electronic configuration is 2s2, 2p4, that is all put together 4 and 6, that is, so all put together it becomes 6. Now, since it is more than 4, it has to be subtracted from 8, 8 minus 6 it gives 2. So, the valency of oxygen is 2. So, second one is oxidation state. It is a charge acquired by an atom assuming electrons are completely transferred based on electronegativity. So, it is completely based on the charge, whether it is a positive charge or a negative charge. Let us see with the example, that is oxygen difluoride. We know that oxygen will gain electrons and possess negative charge, but here in this case it is totally different. The order of electronegativity is fluorine, it is greater than oxygen, which is greater than again for sodium. Now, here the charge of fluoride ion will be -1, which is of most electronegative. So, that is why electrons will be pulled from fluorine towards the oxygen. So, oxygen must balance 2 of fluoride ions. So, that is the reason oxidation state of oxygen is +2. Here it acts as a cation because of the electronegativity property. When it comes to sodium oxide, that is Na2O, Here oxygen is more electronegative compared to oxygen. So that is why oxygen will behave as an anion with -2 charge, and each sodium loses 1 electron to oxygen and forms sodium oxide. Now what happens to the general trends, that is across a period valence or oxidation states change systematically with outer electrons. For example, in the second period, that is from elements starting with lithium to fluorine, lithium will have +1, beryllium +2, boron +3. So when it comes towards fluorine atom, it changes from metallic property to non-metallic property. Down a group, valence remains same due to same outer electronic configuration. That is why all group 1 elements show +1 oxidation state and all group 2 elements show +2 oxidation state. So fifth chemical property is variable valency, that is many elements, especially transition metals and actinides, show variable oxidation states. For example, iron with the symbol Fe shows +2 and +3 oxidation state. It will have 2 different oxidation state. Coming to copper, it will also possess 2 different oxidation states, that is +1 and +2. It is due to availability of D and F orbitals in bonding. So that is again depends on the electronic configuration. Now anomalous properties of second period elements, that is there are few exceptions apart from having these physical and chemical properties, that is the first elements of each group, that is lithium is the first element for the group 1, beryllium is the first element for the group 2 and so on, shows different chemical behavior compared to the rest of the group. Now let us see with the examples. Lithium forms covalent compounds unlike other alkali metals like sodium and potassium, which form mostly ionic compounds. So lithium will form covalent compounds, it is not going to form ionic compounds like sodium and potassium. Beryllium also again it forms a covalent compounds, it is not like, they do not form ionic compounds like magnesium and calcium. So that is about the covalent nature and the ionic nature. There is one more property, that is diagonal relationship. Due to similar ionic radii, polarizing power and electronegativity, what happens is the elements show properties similar to that of elements that are placed diagonally down to it. For example, lithium has properties similar to magnesium, beryllium has properties to that of aluminium, and boron has properties similar to silicon, and goes on. So it is only up to period 2 and period 3. So this special kind of properties are called as diagonal relationship between the elements that is lying in period 2 and 3. Okay, now we shall learn about chemical reactivity, what happens across a period and down the group. Across a period, that is from left to right, so atomic radius decreases, ionization enthalpy increases, they both are opposite, electron gain enthalpy becomes more negative. As a result, group 1 elements, that is alkali metals, are highly reactive, they lose electrons and they act as strong reducing agent. From right side, that is of halogens, they will also be highly reactive, so which can gain electrons from the other elements and that will act as a strong oxidizing agent. Now the elements that lies at the center, that is p block metals and metalloids, so they will be least reactive. So metallic versus non-metallic character, alkali metals have strong metallic character and halogens will have strong non-metallic character. So metallic character decreases across a period while non-metallic character increases across a period. So what happens when elements react with oxygen? So what will be the reactivity with oxygen or oxides basically? Oxides formed at the extremes of a period show opposite nature. So left side oxides would show basic property, that is sodium oxide that reacts with water will give sodium hydroxide which will act as a strong base. Right side oxides will behave acidic in nature. This Cl2O7 reacts with H2O to form hydrogen perchloride which will act as a strong acid. So middle oxides will be amphoteric in nature or neutral in nature, that is aluminum oxide or arsenic oxide will be amphoteric in nature. Otherwise carbon monoxide, nitrogen oxide, nitride oxide will be neutral in nature. Now along a group, that is down the group, that is from top to bottom, atomic or ionic radii increases, therefore ionization enthalpy will decrease. For that, electron gain enthalpy becomes less negative. As a result, metallic character increases down the group and then non-metallic character decreases down the group. For example, when it goes from lithium towards sodium and down potassium, it becomes very strong metals showing metallic property that will have stronger reducing nature down the group. When it comes to other group having fluorine, chlorine, bromine and iodine, that is halogen group, so the oxidizing power will decrease for these kind of halogens down the group. So this was about classification of elements and periodicity in properties. I hope you have understood this session and thank you.